3, 2, 1. Dr. Payam.
Hello, thank you for watching. Today I will present a linear algebra topic that confused the hell out of me when I was an undergrad. And I'm hoping maybe not to give you the full theory of it, because that would take 3 hours, but just present you some special cases that will at least maybe help you with the computations. So that topic is the Jordan canonical form, and Michael Jordan, if you're watching, this is for you. Unfortunately, it doesn't have to do with Michael Jordan. It's Camille Jordan who came with this. And what's the goal? And here we will focus on 3 by 3 matrices. Goal, put a 3 by 3 matrix in one of the following forms. Either a diagonal matrix, like something that looks like star, 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 and everything else is 0. That's diagonal, which is really the best possible case, and I will talk about that. But it turns out sometimes you cannot put a matrix in this form, but you can still put it in most cases in some other forms. Maybe something where the diagonal terms can be whatever, but where all the other terms, well, they're not always 0, but most of them are, except maybe for a couple of ones. So, and this thing where you have a star and a 1, we call this a Jordan block. And let me tell you another scenario. Maybe star, 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 where everything below the diagonal is 0, but just all the entries exactly above the diagonal, they're 1. And those cute blocks with stars and 1, as I said, we'll call them Jordan blocks. Let me guide you through some examples of all the possible scenarios that could happen. First example, best case scenario. Unfortunately, not always happens scenario. So best case scenario. Suppose you have the matrix A, which is 4, 0, 1, 3, 2, 3, 2, 1, 0, 4. Suppose you find the eigenvalues. So eigenvalues. Which means you solve determinant of A minus lambda I equals to 0. Again, I will not do this computation because otherwise this video will be too long. But let's say you do this, you find that lambda equals to 5 and lambda equals to 3. Once you find the eigenvalues, you find the eigenvectors. So for both of them, for both eigenvalues, you find the corresponding null spaces. So lambda equals to 5. If you find the null space of A minus 5i, suppose you do this and you find that it's the span of 1 to 1, and then for lambda equals to 3, suppose you do the null space of A minus 3i, and you find after some calculations that you get the span of 0, 1, 0 and minus 1, 0, 1. This is amazing because you found 3 eigenvectors, so 3 linearly independent eigenvectors, and you have a 3 by 3 matrix. So this is great. So 3 linear independent eigenvectors. Yay! That's where like fireworks should like come into your mind, because this is really the best possible scenario. Why? Because you can just put your matrix in diagonal form. Namely, if you have D equals to the matrix of eigenvalues, so 5, 0, 0, 0, 3, 0, 0, 0, 3, and P be the matrix of corresponding eigenvectors. So for 5, you put the eigenvector corresponding to 5, so 1, 2, 1. And for 3, you put the two other eigenvectors, doesn't matter which order. Okay, 1, 0, 1, 0, minus 1, 0, 1. And then you get, in fact, by a theorem, that A equals to PD inverse. And this is the case where we say A is diagonalizable. Namely, we can transform A into a diagonal matrix. This is great, but as I said, it won't always happen, especially on your exams, it might not happen. And let's see what happens, in other cases. So, what about the following example? A equals to 1, 1, 1, 0, 1, 0, 0, 0, 1. Well, you might say, hey, it looks like a Jordan block. Not quite, because for Jordan blocks, this has to be 0. It's only values exactly above the diagonal that could be 1s. Okay, but let's see where the problem is. Let's find the eigenvalues. Determinant of A minus lambda I. You do this, not hard, because this is upper triangular, and you get that lambda equals to 1. No need to despair. It could happen, it will not happen, that you could still get 3 eigenvectors, 3 linearly independent eigenvectors. But let's see. Let's find the eigenspaces. So null space of A minus 1i, that's, if you do this, let's say you get the span of 1, 0, 0, 0, 1, minus 1. Oh no! How bad? We only have 2 eigenvectors. Let me draw a shocked face. The scream thingy, like the scream emoji, okay? But wait, what does that tell us? It tells us you cannot put this matrix into a diagonal form. But let's see, we can still put it in a Jordan form, which is slightly better. But now let's maybe analyze this Jordan form a little bit. So suppose you can put a matrix in this form. Let's say lambda 0, 0, 1, lambda 0, and whatever, some junk here. And suppose the first vector is v1, and the second vector is v2. By definition of a matrix, what that tells us is that if you want in the basis v1, v2, and maybe v3, we have that A of v1, it's lambda v1. This already tells you that v1 has to be an eigenvector, which means we have to choose one of those two. Okay? On the other hand, let's see what this means. Well, technically, this means that if you apply A to v2, so the second column, you get 1 times the first vector plus lambda times the second vector, which is v1 plus lambda v2. Let's rewrite this. You get A v2 minus lambda v2 equals to v1. In other words, A minus lambda I v2 equals to v1. And this is very, very important. First of all, notice this A minus lambda I appears again. And remember the following. v1 is an eigenvector. Right? It's given. What does that tell us? It tells us that to find v2, you have to solve the following equation. A minus lambda I, that's given, what you want to find, equals to an eigenvector. Which means, exactly this. It's given an eigenvector, you have to sort of back solve this equation to get another vector for a Jordan block. And so let's do this. We need to solve A minus lambda I times blah equals to eigenvector. This is the magic equation, if you like. Okay, well look, sorry, go back to this equation. Here we really just have two eigenvectors. So basically, let's just start with one, and let's see if we can back solve it. If we can, great, we found another Jordan vector, if you want. Okay, so how about, let's start with V1 being 1, 0, 0, and solve, let B1 be 1, 0, 0, and solve A minus I, so maybe my A minus the eigenvalue, which is 1, I, V2 equals to V1. Again, remember we want to find this. Okay. And again, by the way, it's completely random why it shows 1, 0, 0. You could have tried with the other one, but you will see the other one has no solution. But the nice thing is, we've already, in the process of finding the eigenvectors, you already found A minus I. So suppose you do this, and you get 0, 1, 1, 0, 0, 0, 0, 0, 0, V2 equals to 1, 0, 0. If you do that, you indeed get a solution. Namely, if you Gaussian eliminate, you get V2 is 0, 0, 1 plus X, 1, 0, 0 plus Y, 0, 1 minus 1. And it turns out all this is just garbage. You just need one of them because you just need one vector. So how about we just choose the easiest one, 0, 0, 1. So again, let V2 be 0, 0, 1. And again, that's great because it tells us that A has the following form. So it tells us already that A has the form, so it can be put in the form. Again, eigenvalue 1, 1, 0, 0, 0, and the above thing is 1. Sorry for using 1, but if the eigenvalue were 2, it was 2, 2, 1. And some other junk. But look, for the rest, we can just use the other eigenvector. So let V3 be the other eigenvector, 0, 1, minus 1. And then what this really tells us is that the last term can be put in the just diagonal form, 0, 0, 1. In other words, so if you let P equals to V1, V2, V3, which is 1, 0, 0, V2, 0, 0, 1, and 0, 1, minus 1, then, before we had A equals to P dP inverse, but now, since we're talking Jordan, we want to say A equals to P JP inverse. That's like peanut butter and jelly. Okay. Then J equals to, again, the matrix 1, 1, 1, except there's this additional 1 here. Wonderful. Okay. Just one more comment, because, so here we've picked one eigenvector, and we solve A minus I v2 equals to v1, what if we pick the other eigenvector here, okay, 0, 1, minus 1, what would happen if we did this procedure? We would find that the equation has no solution, which tells us that since the equation has no solution, this vector doesn't work. So really the general procedure is find the eigenvectors and just back solve as much as you can. If the one vector doesn't work, just try out the other vector. That's why I'm saying this method isn't quite rigorous, because it turns out there's this theory which tells you exactly what vector to pick, but to be honest, that just went over my head. Last but not least, we're not quite done, sorry, but what about the other case, the more general case? Well, let me see, which blackboard can I use? This one? What about the worst case scenario? Example 3. What if you have A equals to, and it's minus 1, minus 1, 0, minus 1, 0, 0, minus 1, minus 2, 0. Again, not a Jordan block, because those numbers need to be 1. So it doesn't count as Jordan block. So let's see you do the eigenvalues, then you find lambda equals to minus 1. And for the eigenvectors, null space of A minus lambda I, let's say you have the span of 1, 0, 0. This is horrible, because we only have one eigenvector, so for sure it's not diagonalizable. And also, we couldn't use the technique before. But it turns out, even with one eigenvector, you can still put it in Jordan form. Yay! And by the way, some people like to use lambda I minus A. This technique only works with A minus lambda I. Otherwise, it's just messed up. Okay. What does it tell us? It tells us really already that the Jordan canonical form must look like this. Minus 1, 0, 0, and then minus 1, 0, and again, because we have just one repeated eigenvector, and everything above already has to be 1. Okay. What does that mean in terms of what we're trying to solve? Technically, if we let v1, v2, and v3 be the three vectors, it tells us already that a v1 equals to minus v1, which already tells us that v1 has to be an eigenvector. Which means that you have to pick v1 to be 1, 0, 0. Alright, let's continue. What does that mean? It means that a v2 equals to v1 minus v2. v1 minus v2, and just as before, you can reorder this equation, and you find a minus 1i, v2 equals to v1. But that's great, because it's basically the same procedure as before, because this is an eigenvector, and this we want to find. Again, so you have to back solve again. What about the last part? Well, it's actually pretty similar. A v3 will become v2 minus v3, which again tells you that a minus 1i v3 equals to v2. But look, you already know v2 from this equation, which means all you need to do is, again, back solve this equation to find v3. Okay, this is 1 to find, and this is given. So you see, you have to back solve a lot of stuff. And in fact, let's do that. Okay, so let's do this procedure. So as I said, V1 is the eigenvector, 1, 0, 0. And then to get the other one, solve A minus lambda I. Again, it's always A minus lambda I. V2 equals to this chunk, 1, 0, 0, which tells you 0 minus 1, 0, 0, 0 minus 2, 0, 0, 0. V2 equals to 1, 0, 0. You solve that stuff, and you get x times 1, 0, 0 plus 0 minus 1, 0. Again, forget that because we want a particular solution. And very important, do not scale this. Do not write 0, 1, 0 because it'll just ruin your thing. It'll ruin your night. So this is our V2. Great. Now that we have V2, let's solve for V3. A minus minus 1i. V3 equals to this V2. So 0 minus 1, 0. Again, I want to emphasize you just put this vector here. And again, it means solve. 0 minus 1, 0. 0, 0 minus 2. 0, 0, 0. V3 equals to 0 minus 1, 0. Tells you that V3 is x times 1, 0, 0. Get that. Plus 0, 0, 1 half. This is fantastic because it tells you, we're basically done, it tells you that if you define P to be all the matrix of all the vectors that we found, okay, so P is the matrix V1, V2, V3, and important, the order does matter right now, so it's 1, 0, 0. 0 minus 1. 0 and 0, 0, 1 half. Then A equals to PJ P inverse, where J is the full matrix of minus 1, minus 1, minus 1. So the eigenvalue, and you just put 1 above everything. So those are all three cases you can get for 3 by 3 matrices. It turns out that this method actually also works for bigger matrices. Namely, what do, you find the eigenvalues, you find the eigenvectors, and then you just back solve. If something doesn't work, you just stop, you just use the other vector, you back solve as much as you can until you basically get as many vectors as the size of your matrix. And I have a little joke for you at the end. What did the linear algebra motivational speaker say to his audience?
I have no idea.
If I can do it, so can you.
Ah.
And I believe you can do it.
Wow, nice.
Thank you so much.